Welcome to ALP Chemistry on Video, and today's lesson is on Chapter 8 of Zumdahl, which is about chemical composition. And in this live recording today, we've got Crystal with us, and I think Rachel's going to jump in a little bit as well. So if you hear me pause to answer some questions, then that'll be for Crystal and Rachel. Let's get in the lesson. So, what this chapter is mainly about is counting atoms. And atoms are really small, and there are a whole lot of them, so you can't just count them individually. We don't have microscopes small enough to do them. You need really sophisticated equipment to actually see an atom before you could count it. And even if you could, there are so many of them around us, you'd spend your lifetime trying to count them. So normally what's done to count atoms is to weigh them. So you weigh your sample, and if you know what the mass of an individual atom is, then you just take the mass and then divide by the weight of an individual atom. That gives you the number of atoms. So that leads us to the start for this chapter and basically what the average mass of an atom is. Let's start by thinking about carbon. If you think about carbon, its atomic number is 6, which means that it has 6 protons in its nucleus. And it turns out that what makes an element is the number of protons. So the periodic table is organized by atomic number, which is the number of protons in the nucleus of an atom. So what makes an element is the number of protons. The number of neutrons can vary, the number of electrons can vary, but it's the protons which make it that particular element. So if you have an atom that has 6 protons, let's say you have another atom, let's say you have one atom that has 6 protons, 6 neutrons, its mass number will be 12, because protons and neutrons weigh 1 atomic mass unit. So if you had 6 protons, 6 neutrons, the mass would be 12. If you had 6 protons and 7 neutrons, the mass would be 13. And that would be a different isotope of carbon. But it's still carbon, because it's still got the same number of protons. What the number of electrons do is change the charge. So if you have more than 6 electrons, you'll have a negative charge. If you have less than 6 electrons, you'll have a positive charge. So if we take carbon, it's always got 6 protons, but the number of neutrons can vary. With carbon, there are 2 naturally occurring isotopes. There's carbon-12, and in carbon-12, as I said, you have 6 protons and 6 neutrons, which gives you a mass number of 12. And Rachel has a question. Go ahead, Rachel. And Rachel needs a calculator, so here is a calculator for Rachel. And if you're watching on video, you'll need calculators too. So you might need to pause and get your scientific calculator out. So as I said, carbon-12 has 6 protons and 6 neutrons. Carbon-13 still has 6 protons, but now has 7 neutrons. If you were to go out and count the number of carbon-12 atoms out in the Earth, you would find that 98.93% of them are carbon-12. And the remaining 1.07% would be carbon-13, adding up, of course, to 100%. So to get if you take any one particular atom, it's going to be either carbon-13 or carbon-12. But we kind of need to know what the average is, because if you grab a whole bunch of atoms, you're going to have carbon-12, carbon-13 mixed together. We need to calculate an average so we know what the average weight of a particular carbon atom is, so that we can use it to count atoms. So if we were just to take 12 mass units and 13 mass units and calculate an average like we normally do, add the numbers together and divide by the number of numbers we're adding. So we would add 12 and 13 and then divide by 2, and you get 12.5. So we could use that as an average for the mass of carbon. The problem with that is it's not really very realistic because most of the atoms that are out there are carbon 12. They're not carbon 13. So 12 and a half wouldn't give us a very good estimate of the weight of a carbon atom. So instead of calculating an arithmetic mean, which is the normal way we calculate an average, what they do is calculate something called a weighted average. And by weight here, we're not talking about weight as in mass. Weight in this case means importance. And when you calculate a weighted average, what you do is you multiply the importance by the number. In a normal arithmetic mean, every number has equal importance, but in a weighted average, not every number has equal importance. And in fact, when I calculate your marks, I actually use a weighted average to calculate your module mark, because what I do is I say that your outline is worth 5%, so the mark you get for your outline I multiply by 5%, and then your assignments are worth 10%, so I multiply the mark you get on the assignment by 10%, and so on until you get everything added up. And it ends up adding up to 100%, but not every mark in the module has equal importance. So tests are worth more than assignments in terms of your module mark. If you want, I can show you that on your grade sheet later. Let's calculate a weighted average mass for carbon. So what we do when we do this is we're going to take the importance, which in this case is the abundance. We're going to multiply it by the mass in AMU and then divide by the total of the abundance. So what that looks like is we take 98.93% times the mass for carbon 12, which is 12.00000 AMU. And that isn't coincidence that it's exactly 0. They've actually set the system of atomic masses up so that carbon is the standard and it weighs exactly 12. And then we add that to put the decimal a little lower, 1.07% times the atomic mass for carbon 13, which is 13.003354. And then we divide that by the total of the importance numbers, which are the abundances. And when you do that, we will get the atomic mass, the average weighted atomic mass for carbon. And so what I'd like you to do is go ahead and do that now. So take 98.93 times 12 plus 1.07 times 13.003354, and you can just divide that by 100 because 98.93 plus 1.07 is equal to 100. And tell me what you get when you do that. 1,187 doesn't sound right to me. Probably should try that again. So it should be 98.93 times 12 plus...
Do I put in all the zeros?
You don't need to put in all the zeros on the 12. Plus 1.07 times 13.003354, and then do an equals. Now divide by 100. And what do you get?
12.01.
That sounds better to me. 12.01 0735 something. 89. And if we were to round this off to significant figures, using the numbers that we have, let me think, 3 sig figs, 4 sig figs. What would that work out to? I'd have to work that out. I think it's going to work out to, if we were to round it off, 12.011, and that would be the AMU for one atom on average. It's an average mass. Now, grab your periodic table and find the atomic weight of carbon in the periodic table. Look at that, 12.011. It's the same. So this is how they calculate the atomic weights in the periodic table. They use a weighted average to do it. So when you look at the atomic weights in the periodic table, remember that's not the weight of every atom. That's an average weight that you're taking for the atoms, all the atoms of the naturally occurring isotopes. Now, although I've showed you this, I'm not actually going to require you to calculate it. I want you to know where these average atomic masses come from, but on an assignment or test, I'm not going to actually get you to do it. I just want you to know where they come from. And introduce you to the idea of a weighted average, because it comes in handy for calculations sometimes. So the point of all that was that the atomic weights in the periodic table are the weighted average, and they are the mass of one atom in AMU. So ignore the third column for a moment. Let's look at just the first two. So if you have the element carbon, as we've done, we've actually calculated it, the mass of one atom in atomic mass units, and an atomic mass unit is the weight of one proton or one neutron. The weight of carbon is 12.011 AMU. That's the average for one atom. For iron, it is 55.847 atomic mass units on average for one atom. And if you go find iron in the periodic table, you'll find that's the atomic weight that's listed for it. For lead, the atomic weight listed is 207.2 atomic mass units. So lead being number 82 in the atomic number. Now let's put this third column on hold for a moment. We'll come back to it, and we're going to go jump ahead a page, and we're going to talk about the mole. Now, if I was to ask you, if you had, say, a dozen candies, how many candies would you have? You would have 12, correct. You'd have 12 candies. If I said you had a pair of socks, how many socks do you have? Two. If I was to say that you had a trio of musicians, how many musicians would you have? Not for a trio. You'd have three. Three is a trio. So these numbers, a pair, a trio, a dozen, are what are counting units. And what they do is they make counting a little easier for us. So if you had 36 oranges, you could say you've got 3 dozen. And that reduces the number of things we have to think about. We can reduce it from 36 down to 3. A mole is also a counting unit, and it does the same thing. There are a whole lot of atoms around us, but we can reduce the number of things we have to think about if we group them together in a counting unit. And that's what the mole is. And instead of being 2, 3, or 12 things, a mole is 6.02 times 10 to the power 23 things. And that is a freaking huge number of things. But there are a freaking huge number of atoms around us, so we need a big counting unit. So that's why it's a number that's so big. And this number is called Avogadro's number, presumably by the guy who came up with the idea, Avogadro. And you look at that number and you go, that's a really strange number. Why would you choose that number? Because you'd think he could have chosen an easier number to work with. Like, why didn't he choose 1 times 10 to the 23? Or maybe 1 times 10 to the 20th? 23 is kind of a weird number to choose. 6.02 is a weird number to choose. And there is a reason for choosing that particular number. And the reason is that if you have that number of things, the mass of that number of things in grams will be the same number as the mass of an atom in AMU. So if you have a mole of atoms, which is 6.02 times 10 to the 23 atoms, then the mass in grams will be the same as the mass of one atom in AMU. What that looks like is, now we can go back to the previous table, and we had seen that carbon, on average, the weighted average of carbon for one atom is 12.011 AMU. Well, if you have a mole of carbon atoms, in other words 6.02 times 10 to the 23 carbon atoms, you have 12.011 grams. We looked up in the periodic table, found that on average one atom of iron weighs 55.847 atomic mass units. Well, if you have a mole of iron atoms, they will weigh 55.847 grams. And for lead, one atom of lead on average weighs 207.2 atomic mass units. A mole of lead atoms weighs 207.2 grams. That's why they choose that weird number, 6.02 times 10 to the 23 for the mole. So remember that the atomic weights that you read in the periodic table actually have a double meaning. They're the atomic mass units for one atom. They're the grams for a mole of atoms. And this is the definition that you'll use most often for the rest of this chapter. This one, grams per mole. So when you look at the atomic weights in the periodic table, most of the time you're going to be using grams per mole for them. So we'll start doing that. Now, before we do that, I just have a question that I ask students frequently, just to get them into the idea of the mole. So if you had a mole of boron atoms, how many atoms would you have? 6.02 times 10 to the 23 atoms. If you had a mole of cobalt atoms, how many atoms would you have? 6.02 times 10 to the 23. If you had a mole of water molecules, how many water molecules would you have? 6.02 times 10 to the 23. So remember, that's how many things are in a mole. And once we get into the calculation, students often forget that, and I have to come back to it. And they often forget that. So lock that in your brain, that is the number of things in a mole. And it doesn't matter what things we're talking about. Could be atoms, could be molecules, could be bowls of jello. If you have a mole, it's 6.02 times 10 to the 23 things. Okay, so we know that if you look in the periodic table, you can get the grams per mole for an atom. And this is something called molar mass. Molar mass is the grams for a mole. And we normally write it in units of grams per mole, or G over MOL. They abbreviate mole as MOL, saves us writing one letter. You'd think they might have shortened it a little more than that, but that's the way it is. So MOL is the abbreviation for a mole. And so the molar mass of iron we write as 55.847 grams per mole. Okay, now I'm going to introduce you to something called a mole map. And most of the calculations for probably the next 3 chapters will involve mole maps. And this is something that I came up with. It's a way of helping students to see what steps are needed in the chemistry calculations. So a typical problem you might have, which would use a mole map to solve, is if we had 10 decimal grams of helium and we wanted to know how many helium atoms we'd have in that 10 grams of helium. The way you use a mole map Well, let me describe the mole map to you before we get into using it. First thing, to draw a mole map, what you do is you connect a G to an N, and then an N to a P. So G and P. And the G stands for grams. The N is for number of moles. And I used to use M for moles. The problem with using M is that people often use M to stand for mass. And if I start using M for moles, people will start getting confused over whether it's mass or moles. And N in chemistry is often used to stand for moles. So I just thought I would use it here. So you'll have to remember N stands for number of moles. P is for particles. And by particles, what I'm talking about are atoms and molecules. And there is, as you can see, or there are, as you can see, two sides to the mole map. So you have a GNP on one side and a GNP on the other side. And the reason there are two sides to the mole map is that there are chemistry calculations that will often deal with two different substances. In the problem I've given you, and I think all the problems in Chapter 8 of Zumdahl on chemical composition only deal with one substance. So since we're only dealing with one substance, the calculations in Chapter 8 will really only use one side of the mole map. We'll only get to the other side of the mole map once we get to Chapter 9. So in the next lesson for Chapter 9, we'll be using two sides of the mole map. So here's how we use the mole map. First thing is to label the mole map with the substances that are involved in the calculation. In this case, we've only got one substance. It's helium. So beside one of the N's, we put an HE to stand for helium. And that identifies the side of the mole map. That side of the mole map is going to be the helium side. In this case, we only have one substance, so we're not going to need the other side of the mole map. We can just X that out. The next thing is to look and find what information has been given in the problem. Well, the problem tells us we're starting with 10 decimal grams. So we want to put that on the mole map, and where it goes is on the helium side, and we put it beside the G for grams. The next thing to do is to try and figure out what the problem is asking us to calculate. And it's asking for how many helium atoms. And we need to think about, well, where does that go on the mole map? Well, if we're looking for numbers of atoms, that goes with the P for particles. So we put a question mark beside the P, and I usually write the unit that we want to atoms. And now the calculation that we're going to set up, we can see the number of steps and the order they have to be done. It's going to be a two-step calculation, and the order is going to be start at grams, calculate moles, and then for moles, calculate atoms. So it's going to be a two-step calculation, and this is the order, and we're going to start from 10 decimal grams. Now at this point, having done Chapter 2 on measurements, you're familiar with unit conversions now. And we make use of serial unit conversions, converting one unit to another unit to another unit to get our answer. So we're starting with 10 decimal grams of helium. We know it's a two-step calculation, so we're going to need two conversion factors. And the target, we know, is going to have units of atoms of helium. In the first step of the calculation, we're going to have to get rid of grams. And with these calculations, generally, the unit you start with is going to go in the bottom, always, because we're going to get rid of it. So we have to get rid of the grams of helium unit. At the end of the first step, we're going to be here, beside the N. That'll be moles of helium. So at the end of the first step, the unit will be mole of helium. So that goes here. In the second step, we have to get rid of that unit. So mole of helium has to go in the bottom. And at the end of the second step, we'll be at P, and the unit will be atoms of helium. Now, if we check our units, we'll find that grams will cancel. And what I mean by cancel is that you can treat units as if they were numbers, like you did in converting units in Chapter 2. So if you had 2 times 1 over 2, that is 2 divided by 2, and your 2's cancel, leaving you with a 1. So we're doing the same thing with the units. So that grams will cancel. Moles can cancel. And the only unit we're left with is atoms. And that's good because that's the unit we want to end up with. So now we've got our units in. The next thing to do is to put numbers that go with these units. Grams per mole of helium. Where do you think we can find that? It's not 6.02 times 10 to the 23. On the periodic table. Right. So find helium and find the atomic weight of helium. 4.002602, and that is grams for 1 mole. So 1 mole goes on top, grams goes on the bottom. So let your units guide you in terms of where the numbers go. It's always grams for 1 mole. Now we need the atoms for 1 mole. How many of atoms in a mole of helium? You said it the first time. How many atoms in a mole? You said it the first time.
6.02.
Right. See, students do forget.
Yeah.
6.02 times 10 to the 23 atoms in 1 mole. So it turns out when you do these calculations that when you're going between G and N, you need the molar mass, because molar mass is in units of grams per mole. So that will be the conversion factor, which will take you between G and N. When you're going between N and P, you'll need Avogadro's number. You'll need the 6.02 times 10 to the 23, because that has units of either atoms per mole or molecules per mole, and that's the conversion factor that you'll use to go between N and P. So to do this calculation, you're going to do 10 divide by 4.002602 times 6.02 times 10 to the 23. So go ahead and do that calculation and let me know what you get.
Oh, so we do 10 divided by?
Will be 10 divided by. So again, we don't have to do the times 1. It'll give you just 10. So just do 10 divided by 4.002602. 6.02 EE23.
1.50402164
times 10 to the 24. And we'll have to round that off for significant figures.
Can you teach me how to find this amount of significant figures?
So to find the significant figures, we look at each number in our calculation. In the 10, how many significant figures do we have in the 10? Actually, there's two significant figures because we have a decimal. Right. If there wasn't a decimal, it would be one sig fig. Because we have a decimal, that's two sig figs. We look at the 4.002602 grams. That's 3, 5, 7 significant figures. And that's way more than the 2 that we had on the 10 decimal grams. The 1 in the 1 mole, that's exact. It's exactly, that's of definition. It's that number for exactly 1 mole. So we don't have to worry about significant figures on the 1 mole. We consider that to be infinite. Same with the 1 mole on the bottom. We consider that's exactly 1 mole. So it has infinite significant figures. And the 6.02 has 3 significant figures.
So now, say if it was 6.00, would it have 1? Does the trailing zeros don't count?
Trailing zeros count if there's a decimal. So if it was 6.00, that would be 3 significant figures.
I keep getting that mixed up.
So the smallest number of significant figures, looking at all our numbers, is the 2 significant figures that were on our 10 decimal grams of helium. So our answer should have 2 significant figures. So that means we're going to round at the 5. So we look 1 to the right, it's a 0, which means we don't have to round the 5 up. So we're going to write 1.5 times 10 to the 24 atoms. Way to go, Rachel. Yeah. Okay, so now that we've done that one, here's another. So let's practice this one. So what we're going to do is to first thing do a mole map. So we do GNP. So that's our mole map. So to remember the mole map, all you need to remember are 3 letters, GNP. And remember grams, moles, particles. So we look at what information has been given in the problem. What substances are involved in this problem?
So we have 7.23.
We have 7.23 times 10 to 25 atoms. That is going to go with our particles, right? But what substance do we have? What substance are we dealing with first before we put that on? We're dealing with gold. And we're going to put that beside the N, just to take note. Are there any other substances in our calculation? No, and in this chapter there won't be. So we don't need the other side of the mole map. And most of the time in this chapter you won't. I think all of the calculations in this chapter you won't. Okay, now we can put on the number of atoms, and that goes with the particles, like we said. So 7.23 times 10 to the 25, that goes down here with the P, 7.23 times 10 to the 25 atoms. And what is it we're trying to calculate?
The amount of moles.
Moles. Where does that go in the mole map?
The N.
Goes with the N, right. So that's where our target is. So how many steps is that going to be in our calculation?
From particles to mole.
Nope, we don't have to go to grams. Our target is moles.
Get moles. Okay. All right. So 1 step.
1 step. It's as easy as that. It's a 1-step calculation. Right. If the question mark was on the G, then it would be 2 steps. Right. So it's a 1-step calculation. We're starting with our 7.23 times 10 to 25 atoms of AU. That's the symbol for gold. It's 1 step, so we just need 1 line. And our target is mole. So the unit that we should have on our answer should be in moles. So what unit has to go in the bottom in our conversion factor? Atoms of AU, so that we can cancel them. So that goes on the bottom. What unit should go on top? Mole, because at the end of our step we will be at the N, and N has units of moles. and that's what we want for our target. So moles will be on top. All right, how many atoms in a mole for AU?
6.02 times 10 to the power 23.
6.02 times 10 to the 23. Does that go on top or on bottom?
Top.
No, it goes on bottom. 1 mole
One mole
is
6.02.
6.02 times 10 to the 23 atoms. So remember, whenever you're going between N and P, you need 6.02 times 10 to the 23. If you were going between G and N, that's when you need the molar mass. So here's your calculation. 7.23 EE25 divide by 6.02 EE23.
One 120
120.
point zero
0.099, and that's probably all we need. So you can stop right there. And now we need to do our sig figs. So how many sig figs in 7.23 times 10 to the 25? 3. How many sig figs in our 6.02 times 10 to the 23? 3. So how many sig figs should be in our answer? 3. So what should we round our answer off to? 120. And that is 2 sig figs.
120.1.
No, just 120 decimal. Now it's 3 sig figs. And we need one more thing before we can finish. What do we need?
We need our mole.
We need the mole. You're right. Because a number without a unit has no meaning.
Has no meaning.
Right. And it's helpful on tests and assignments if you just underline your answer or put a box around it or something just so I know where your final answer is. Okay. And we've got a bunch more problems. Let's just do one more unless you want to do a couple of them. So pick one of these 3 and we'll do one of those. Which one would you like to do?
Well, I know if we do 2, it's only 2 steps.
Ah, you're thinking ahead. You know that number 2 is going to be 2 steps?
Yep.
So let's do question 2. Okay. We have 100 decimal grams of iron. We want to know how many moles. So first thing is always set up a mole map. And we're only dealing with one substance. So we only need a one-sided mole map. So what's our substance?
Iron.
So we'll put that beside our N. What information has been given?
100 decimal grams.
100 decimal grams. Where does that go in the mole map?
Grams.
Beside the grams. So 100 decimal grams. Where's the target?
Moles.
Moles. Where's that in the mole map?
Where the end is.
Where the N is. So we're trying to get to mole. How many steps in our calculation?
Uno.
Just one. Uno. One step. From G to N. So we set up our calculation. How do we set up our calculation?
We're going to go 100 decimal grams.
100 decimal grams
Line.
times a line. That's where our conversion factor is going to go.
Put gram on the bottom.
Now before we do that, let's put an equal sign and our target,
Mole.
which is mole. And if you do that, that just helps you keep in mind where you should be ending up. So it's grams of Fe. Now in this chapter, because we're only doing one-side mole maps, it's less important that you put what the substance is that you're calculating. In the next chapter, it will be important because we're going to be dealing with two-sided mole maps, and you'll have one substance on one side, one substance on the other side. So force of habit, I'm going to try to put the substance with the unit every time, just because when you get to chapter 9, you'll need to do that. So on the bottom, Crystal said that we need grams of Fe, because that will get rid of our grams of Fe. At the end of this calculation, what unit will be on top?
Mole.
Mole of Fe. Yep. Sometimes I only put the unit or the substance either on the top or the bottom. I may not put it on both, but I'll put it on at least on one of them. And grams per mole for Fe, where are we going to find that?
Going to go 1
1
over
1 over
6.02
No, it's not going to go 6.02 times 10 to the 23 in the bottom. So Crystal's looking in the periodic table, and she found the grams per mole for iron as 55.847 grams for 1 mole. So remember that if you're going between G and N, you need the molar mass, which you get out of the periodic table.
If you're going between N and P, you need the 6.0.
And if you're going between N and P, that's when you need the 6.02 times 10 to the 23. So to do this calculation, you're going to do 100 divide by 55.847.
One
1.7906. And what should we round that off to?
Should we have? Can you go with the highest amount of sig figs?
Lowest number of significant figures is what we're going around to. So it's 3 significant figures because 100 decimal is 3 significant figures. So what should we round our answer to?
55.8.
No, not 55.8. What's our answer?
Oh, what? 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 What are you talking about? 1.79.
What you talking about, Crystal?
I don't know.
That would be 1.79
1.79.
mole. That's our answer. And just for completeness, I'll just get rid of grams of Fe, grams of Fe, just to clearly indicate that we're left with moles, and that's it. And so it's moles of Fe. Okay, moving on. So now you know that the molar mass is the grams per mole of a substance. And if you need the molar mass of an element, you can get it off the periodic table. If you need the grams per mole, you go to the periodic table, that's where you're going to find it. Read the atomic weight. If it's a compound, you do something similar, but for a compound, you have to add up the molar masses of the individual elements. And for that, you'll need to know the formula. So for example, if you look at water, we know water has two hydrogens and 1 oxygen. If you put a bunch of atoms in a pile, the weight of that pile will be the weight of the individual atoms. So if you have 2 hydrogens and 1 oxygen in a pile, the weight of that pile will be the weight of 2 hydrogens and 1 oxygen. And the same applies to a mole. So if you have a mole of water, then the weight of that mole of water will be 2 moles of hydrogen and 1 mole of oxygen. So if you want to find out the weight of 1 mole, you add the grams per mole for 2 moles of hydrogen and the grams per mole for 1 mole of oxygen. So in this formula, you've got 2 hydrogens, so you take the atomic weight, multiply by 2, and you get 2.01588. In the formula, you have 1 oxygen, so you're going to do 1 times 15.9994 for the oxygen, and then you add those numbers up. And when you add those numbers up, what do you get?
My calculator.
2.01588 plus 15.994. 18.0098. And it's another 8. But the rule for addition and subtraction for significant figures is to round off at the last significant figure, which in this case is that 8. We got a different answer?
Yeah, when we did it before.
When we did it?
I had 18.0153.
Can you check the calculation again for me? And Rachel's answer sounds familiar to me, so I'm thinking Rachel's answer is correct.
I think I forgot to put 1 8 in there. Yeah.
18, so it's 18.01528.
Okay, can you repeat that for me?
18
18
decimal
decimal 01528. Okay. That looks better. But we're still rounding before the last 8. So what should we round that to?
1/8.
1/8 point
Decimal 0.152.
0.15
What's it gonna be?
3.
Yeah, there we go.
There we go.
And why is it like that?
Because the 8 is higher than a 5.
Because the 8 is higher than a 5. Way to go, Crystal.
Yeah.
So the answer is 18.0153 grams per mole. So if we wanted a mole of water, we could weigh out 18.0153 grams, and we'd have a mole of water. And we know that would be 6.02 times 10 to the 23 water molecules. Okay. Let's take a look at chemical formulas. So now you know how to get the molar mass out of a chemical formula. We need to talk a little bit about chemical formulas because we need to be a little more specific when we use a chemical formula. There's actually 2 types of chemical formula. There are molecular formulas and there are empirical formulas. The difference between them is that a molecular formula tells exactly how many atoms are in a molecule. And it shows the exact composition, whereas an empirical formula tells the lowest ratio, tells the number of elements.
I have tells the ratio.
Tells the ratio of elements to each other in lowest terms. Rachel's a pro at this now. And for ionic compounds, we really use which one? The empirical formula. And the reason for that is because ionic compounds don't actually exist as individual molecules. So if we take something like sodium chloride, you don't find individual sodium chloride particles. What you find is one sodium attached to one chlorine, attached to another sodium, attached to another chlorine, attached to another sodium. C2H6 is a little different because C2H6 isn't an ionic compound. It probably would exist as molecules. SO4 again would be covalently bonded, but something where you take a metal and a non-metal, put it together, then that would be an ionic compound. Turns out, although there's a difference in terms of how they're defined, you calculate the formula weight, which is the mass of an empirical formula, you calculate it exactly the same way. So the formula weight, you would calculate just like I showed with the molar mass. So you add up the weights of all the individual elements. So an empirical formula, you call the molar mass a formula weight. For a molecular formula, you can call it a molecular weight, because we actually are dealing with molecules. So the molar mass of a molecular formula is the molecular weight. The molar mass of an empirical formula is the formula weight. In terms of calculations, it doesn't really matter because you calculate them the same way. But you will have to keep in mind the distinction that the molecular formula is exactly how many atoms. The empirical formula is just the ratio of the atoms to each other. So I have an example on the next page to show what that looks like. So glucose, the compound glucose, has exactly 6 carbons, exactly 12 hydrogens, and exactly 6 oxygens in its structure. The empirical formula, we reduce all these numbers to lowest terms. So the 6, the 12, the 6 are all divisible by 6. So we can divide all those numbers by 6, and if we do that, we get CH2O. So that is the empirical formula for glucose. It just tells the ratio of the elements in lowest terms. Formaldehyde already is in lowest terms because you can't divide it down any further. So the empirical formula for formaldehyde is CH2O. And turns out they're the same. You're right. Good observation. For acetic acid, all the numbers are divisible by 2. So what would the empirical formula of acetic acid be?
CH2O.
CH2O. Notice they all have the same empirical formula. The molecular formulas are different, but they all have the same empirical formula. Okay, so now we have some examples of calculating molar mass, formula weight, and let's do the molar mass of aluminum nitrate here. This would be a formula weight. So the formula weight of an empirical formula. Because this is an ionic compound, we're actually calculating the formula weight. How many aluminums do we have in this compound?
3.
Nope, not 3. 1 aluminum. So we have 1 aluminum. How many nitrogens do we have?
3.
We do have 3 nitrogens. How many oxygens do we have?
3.
Nope, not 3.
That's just 3 times 3.
It's 3 times 3. So we have 9 oxygens. So the number outside the bracket we need to multiply by everything inside the bracket. So you need to look up the atomic weight for aluminum. So for aluminum, the reason aluminum is 1 is because the number to the bottom right of aluminum, which we're not showing, would be a 1. So what's the atomic weight for aluminum?
26. 98153.
98153. Okay. And nitrogen?
14.00674.
So it should be 3 times 14.00674. And what's oxygen's atomic weight?
15.9994.
So it should be, 9 times 15.9994. So calculate all those out for me. The top one is just 26.981539. And calculate the other two for me. So what did you get for the second one? 42 decimal.
02022.
So 42.02022. And the last one? 143 decimal 9946. And then you add all those together.
Two
212
decimal
decimal
996.
9966359. And where should we round that? No,
Oh no, we're adding.
because we're adding, so we have to find the last significant figure, which is going to be at this 6 here. And so it's going to be there. There's a cutoff. So what does that round to?
Okay, you confused me for a second, but I'm good. So we're gonna round that to
212.9964.
212.99.
Good. And what's the unit on that? It's molar mass. Grams per mole. It's always grams per mole. When you do this calculation, always grams per mole. So it's a good idea when you do this type of calculation, always put grams per mole in the end. Just to remind you, that's what it is. Okay, so now what we're going to do is a mole map calculation for a compound. So it's the same idea, the only catch being that to calculate the molar mass, you're going to have to add up all the elements to get the molar mass. So in this compound, we've got the formula for THC, which is tetrahydrocannabinol, which is the active ingredient in marijuana. And some people wonder why I ask so many drug questions as my examples. Well, they're just interesting compounds. So it's not that I have a drug thing or anything. It's just that they are interesting compounds. They're practical applications. So okay, so in this problem, we have THC, and let's say we have 20.0 grams of THC, and we want to know how many molecules that would be. So as usual, we set up a mole map, and the substance we're dealing with is THC. What information do we have?
We have 20.0 grams.
Where does that go in our mole map? 20.0 grams. Goes with the G. And what information do we want to get?
We want to get P. Particles.
We want to get molecules, which is at P for particles. So that's where our question mark goes. And how many steps will that be in our calculation?
Two-step problem here.
That's a two-step problem. So we need to go from G to N, and then from N to P. So how do we set up the calculation?
So we'll put 20.0 grams.
20.0 grams, and we'll just put a little THC beside that, just to remind us what substance we're dealing with.
Times line.
Times a line,
Times line.
times another line, because we have a two-step calculation, and then an equals,
Mole.
and we're trying to get molecules
Yeah, molecule.
as our unit. Okay, so what unit will go on the bottom of our first step?
THC.
What of THC?
Grams.
Grams of THC. So that goes in the bottom. At the end of the first step, what unit will we have?
At the end of the first step.
Because we're
Oh, up here, mole.
at the first step, so at the end of the first step, we'll have mole of THC. And what's going to be on the bottom of the second step?
Mole of THC.
Mole of THC, because we have to get rid of that unit. And what unit will we have at the top?
Molecule.
Molecules of THC. Okay, and just checking the units to make sure our units are going to work. Grams cancel, moles cancel, and leave us with molecules. That's good. That's what we want. Now we need to put the numbers in. So how can we get grams per mole for THC?
Atomic mass.
Atomic mass, but this is a molecule. So we're going to have to add the weight of 21 carbons, 30 hydrogens, and 2 oxygens together to get the grams per mole. So we need 21 carbons, 30 hydrogens, is that right? 30 hydrogens? And how many? 2 oxygens? And we know that by now that carbon is 12.011. And if I remember correctly, oxygen, no, not oxygen, hydrogen is 1.00794. And oxygen is 15.
9994.
Rachel's got it, 15.9994.
That's the only number that sticks in my head, though.
Well, we do a lot of calculations involve oxygen, so just the repetition tends to put that one in there. So maybe 5 years from now, you'll still have that piece of information, that random piece of information stuck in your brain.
What is the atomic number for oxygen? Oh, it was like 15.9999.
You never know when that information might come in handy.
Hey, if I have an answer of 0.9996, would that be rounded to 1?
0.9996 depends on how many significant figures you need to keep.
1, 2, 3, 4.
So 0.9961 is 4 significant figures.
0.9996 is 4 significant.
Oh, 0.39s? 0.99961?
0.9996. Because I divided the molar mass by the formula weight, and my answer was 0.
So if you had a number of 0.9996, That is 4 significant figures.
Yes. So then I wouldn't divide it by anything. Would I divide all these answers by that, though? See what I mean?
Oh, so Rachel's question doesn't apply to the one we're working on now. So for those of you watching on video, we're on a complete tangent here. For Rachel's benefit, the answer 0.9996 is close enough to 1 that you'd multiply your empirical formula by 1. So in other words, your empirical formula and your molecular formula are the same.
They're going to stay the same.
Yeah, so you can just write down the same formula as your molecular formula. So Crystal, you got some numbers calculated for me?
I do. 252.
252.
Decimal 231.
231.
30. Next.
Next one is 30.
Decimal 2382.
2382.
Next. 31. Decimal
3199998. 8.
Forget it,
8.
you're on 8.
Having trouble with my 8s. There. And when you add all those up,
It's gonna confuse me. So now do we want to draw the line at the end of the equation?
do we want to draw the line at the end of the equation? Let's add them first, then we'll draw, and then we'll figure out where to round.
The way I remember that, though, is that how many, like when you're adding and subtracting, or adding, sorry, I guess, is how many spaces or how many numbers are after the decimal place.
Correct.
That's what you're going to remember. Like that's how many you're going to. Yeah.
So Rachel is saying how many decimal places, to figure out where we're going to round, how many decimal places after the decimal point.
Or like the smallest number.
Yeah, and so here, for the first number, we're 3 places after the decimal point, second number is 4 places after the decimal point, and the third number is 4 places after the decimal point. So the lowest number would be 3 places after the decimal point. That would be our cutoff. Yeah.
That's how I remember. You know what?
So we'll do that after we've got a number, a
So
total.
the number is 314.
314, decimal, 468, probably a 0.
No, that's exactly it. 314,
And our cutoff is at the third decimal place. So we can drop that last 0. So 314, decimal 468. And what's the unit on that?
Grams per pH. Grams per mole.
Grams per mole. Always grams per mole. So 314.468. So what numbers do we put in our mole over gram in our calculation?
Put 314.
314.468 goes on top or bottom? On bottom, because it's the grams for 1 mole. So 1 mole is 314.468 grams. And how many molecules of THC in a mole? 6.02 times 10 to the 23. Does that go on top or bottom?
Top.
On top. So it's 6.02 times 10 to the 23 molecules in 1 mole. So now we've got our calculation set up. So 20 divide by 314.468 times 6.02 EE23.
My full throttle would be right up there. Woo, I'm like zing.
So this is a
I don't
big,
make
big
that
number.
very often.
Did you get an answer, Crystal?
Yeah, it's big.
It will be big.
3.8.
3.8
2.
2
8.
8
6. 8.
6 8 8.
452.
Probably don't need to go any further than that. Times 10
22.
to the power 22. And then round that off to how many sig figs?
3.
3 sig figs, because 20.0 is 3 sig figs. And so what number should we write down for our answer?
3.83.
3.83 times 10 to the 22, and it's molecules of THC. And that is our final answer. Okay, so we have another example. I don't think we need to do another one, if you're okay with that. You can always do it with me later. Okay, now what we're going to look at is the last thing for this chapter, and that is that if you were given a percent composition, and you would normally determine that by way of experiment. So someone might do an elemental analysis. There are machines that can analyze elements in a substance. And normally what you get out of that would be a percent. So you might say, well, this element is, say, 20% oxygen, for example. And we might say, well, it's 20% oxygen and 70% aluminum, for example. What would be nice to be able to do is take information like that and then be able to make an empirical formula. And if we know the empirical formula, that will identify the substance for us. So, so this is the objective of this chapter, or this section of the chapter. Given a percent composition, or masses, it could be just the masses of the elements, come up with an empirical formula. And by the way, I haven't put percent composition going the other way from a formula to a percent composition isn't in this lesson, but it is in the textbook, and you'll still need to know how to do that. So look for the information how to do that from the textbook, and if you need help with that, let me know. Okay, to remind you, if you have a chemical formula, what that's telling you is the composition of that compound by the numbers of atoms. So in other words, if you have the formula CaCl2, what that tells you is you have 1 calcium atom and 2 chlorine atoms. So far, so good. So this isn't the mass, so it isn't 1 gram of calcium, 2 grams of chlorine. It's numbers of atoms. 1 atom of calcium, and 2 atoms of chlorine. But most of the time when you do analysis, you don't get the numbers of atoms directly. What you're getting is mass, because remember, we count atoms by mass. So if you analyze a substance in a lab, you'll get the masses of calcium and mass of chlorine instead of the numbers of atoms. What we'd like to be able to do is to get the formula from the percent mass. And here's the method for doing it. So for example, let's say we've analyzed an unknown sample, and we found that it contained 66.75% copper, 10.84% phosphorus, and 22.4% oxygen. We want to determine the empirical formula. The first step to do that is to convert our percents to grams. And all you need to do that is just change your percent symbols to gram symbols. Because basically, if you have 100 grams, then that will mean it will be 66.75 grams of copper, 10.84 grams of phosphorus, and 22.41 grams of oxygen. So we'll write those in, 66.75 grams copper. Are you with me there, Crystal?
Sorry, Chris just texted me from the hospital, so I just understand that.
10.84 grams phosphorus and 22.41 grams oxygen. So just let Crystal catch up and write those things down. Once you have the masses in grams, you're going to convert those to moles. And to convert those numbers to moles, it's a GNP calculation. And to go from G to N is just one step. So we have to do 3 separate calculations. So we're going to do 1 for copper, 1 for phosphorus, 1 for oxygen. So we're taking our 66.75 grams of copper, and we need to convert that to moles. We're doing the same for phosphorus. And then we're doing the same for oxygen. We know we've got to have grams in the bottom, and moles will have to be on top so that our grams will cancel. We need the grams per mole for copper. Where can we find the grams per mole for copper?
Atomic mass.
We'll find it from the periodic table, and we'll find it from the atomic weight.
6.3.
6.3 decimal
5.46.
546, and that goes in the bottoms because that on the bottom, that's gram for 1 mole. All right, and for phosphorus, what's phosphorus?
We have 30.
30,
Get ready for a big number. 973.
973,
762.
762, and again that's on the bottom, and that's grams for 1 mole. And then oxygen, what's oxygen, Rachel?
15.9994.
15.9994 grams.
How he writes his nines.
I know.
It's like a little do something.
So we gotta
People complain a lot less about my writing at the smartboard once they've done it themselves, because writing on the smartboard for some reason is just weird, and when students actually try it, they find it's not as easy as it looks. Okay, so try doing these calculations and let me know what you get.
We're just pretty used to Googling numbers, more or less.
So it's just a division.
Just a division, 66.75 divided by 63.546.
Equals 1.0.
1.0
5042.
0. We just need 0 because it's 4 sig figs. Then 10.84 divide by 30.973762.
Is molecular weight the same as molar mass?
So Rachel has a question, is molecular weight the same as molar mass? And molecular weight is a molar mass, but not all molar mass is molecular weight. Because molecular weight is the molar mass for a molecular formula.
Oh, yes.
Formula weight is the molar mass for an empirical formula.
Gotcha.
Got an answer for the second one, Crystal?
Yep. Decimal. No number.
0.34.
34. 99 should be good.
99. Okay,
Is that all we need?
that's all we need. And for the last one, 22.41 divide by 15.9994.
1.4006.
1.4006, so that'd be 01. 1.401, I think, mole.
All we need.
That's all we need. Okay, so now what we do is find the smallest number of moles, and that's our 0.3499. Now we divide each number by 0.3499.
Each number of what?
So each mole. So for copper, we take our 1.050 mole and divide by
Divided by the little one.
0.3499 mole. And for phosphorus, we just divide it by itself. And for oxygen, we take our 1.401. And divide all those out for me and let me know what you get. Phosphorus is obviously 1 because it's just
Yeah.
dividing by itself.
First one, copper, is 3.000.
3.000, which so it's basically 3.
Keeps going, yeah. But it keeps going with like other numbers.
Yep, we'll just leave it as 3.
Yeah, okay, I don't know what I did. There, okay. And then 1.401 divided by 0.3499. 4.004.
So call it 4.004, so we're going to call it 4. And now, our empirical formula has 3 coppers, 1 phosphorus, which, and again, we don't need to show the 1, and 4 oxygens. So the empirical formula is Cu3PO4.
Cool. All right, let's move on there.
So that's how you get an empirical formula.
All right.
Sometimes we want the molecular formula, though. And if we need the molecular formula, to get it, we'll need more information. We have to know what the molecular weight is. And what we'll do is you'll be given the molecular weight. You can calculate the formula weight just by adding up all the elements, the weights of all the elements. And take your molecular weight, which will be given, divided by the formula weight, which we'll calculate from the empirical formula. And that will give us a factor that we're going to use to multiply the empirical formula by. And what I mean by that is if we think about glucose, glucose has the molecular formula C6H12O6. Reducing it to lowest terms gives us our empirical formula CH2O. The factor is 6. So the factor between the empirical formula and the molecular formula is a 6. So in other words, if we were to add the weight of the molecular formula to get the molar mass of the molecular formula of glucose to get the molecular weight, it will be 6 times the empirical formula, because the difference is 6 times the number of atoms. This is the reverse of the calculation that I've just shown up here. So if you were to do this calculation for glucose, you should get a 6. And 6 is the number to multiply the empirical formula by to get the molecular formula. So I have an example for doing that here. So let's say you did this whole procedure to find an empirical formula, and when you did it for a particular compound, you got an empirical formula of CH4. We're given that the molecular weight is 64.20. So we want to find the molecular formula. To do that, we need to calculate the formula weight. So we get the formula weight from the empirical formula. In this case, because it's CH4, how many carbons do we have? 1. How many hydrogens do we have? 4. So we need to add the weights of 1 carbon, which is 12.011, and 4 hydrogens, which is 4 times 1.00794. So we're going to add 12.011, and we're going to add 4 point something. In fact, probably 4.0 something. 316. Add those up, and what do you get?
Sorry, I'm still trying to write the question. 0.1.
16.0426.
26. And what are we going to round that to?
16.043.
Our cutoff is here. So right, 16.043. And what's the unit on that?
Grams per mole.
Always grams per mole. Okay, so now this is our formula weight. So that's our formula weight. And we take our molecular weight, divide by the formula weight. We were given a molecular weight
That's 64.20.
of 64.20. We divide that by the formula weight, 16.043. And what do you get when you do that? Oops.
1029.
That doesn't sound right. 1,000 doesn't sound right.
I think you might have forgot the decimal point and then 6420.
64.20
No, she did it right.
divide by
Times it, honey.
16.043.
I was like, what? No, she has it in there, right?
So that was a multiplication instead of a division.
4.0017.
4.0017, which is about 4.
So that means that we will go up in times the empirical formula. Well, by
So right, now we're going to multiply the empirical formula times 4. So the molecular formula would be what?
4 times 4 would be CH8 or 16.
C4H8.
C4H16.
C4H16 is the molecular formula.
Teamwork.
Yes.
Teamwork.
All right, that is the very end of it.
And
Do this test. I need to do it.
we're at the end. So here's another practice problem. And I'll leave you to do this practice problem on your own. If you want some help doing it, you can come see me. And good luck with Chapter 8.
Eric?